Hello, my name is Bonnie Hutchins, and today we're going to talk about mixture and concentration problems. We'll look at how to understand mixture and concentration problems. We'll set up equations to solve mixture and concentration problems. We'll use various mathematical techniques to solve the equations, and we'll make conclusions about the solutions for the problems. We're going to start with mixture problems. To solve mixture problems, read the problem carefully. We have to decide what we know and what we don't know. Choose a variable and represent the unknown. Choose a variable for one unknown and then write an expression for the other unknown using the variable and one of the facts, or use a different variable. Reread the problem and write an equation or equations using the variables and other facts. Number 4, we're going to solve the equation or the equations, and then we're going to make conclusions based on the solution and the questions asked in the problem. Here's a mixture problem. We're going to read the problem carefully. A chemist has 2 chlorine solutions. One solution is 20% chlorine and the other one is 80% chlorine. How much of each solution is needed to make 15 liters of solution that is 40% chlorine? We're going to decide what is known. We know that the chemist wants 15 liters of 40% solution. The chemist has 20% solution and an 80% solution. What we don't know is the amount of the 20% solution or the amount of the 80% solution. We'll choose a variable and represent the unknown. Choose a variable for one unknown. We chose x. Write an expression for the other unknown using the variable 15 minus x. Or we can use a different variable like y. Reread the problem and write an equation or equations using the variables and other facts. We're now ready to solve this equation. Now we've solved the equation and we can make a conclusion based on the solution. It asks, how much will the chemist need? Well, the chemist will need 10 liters of the 20% solution and 5 liters of the 80% solution. We can also solve this problem using a system of linear equations where we're using x's and y's. In the first mixture, we have x, the amount, plus y, the amount, has to be equal to 15 liters. So we know we want to get 15 liters. In the second one on the right, we have 0.20 x, representing the 20% solution, plus 0.80 y, representing the 80% solution, has to equal 0.40, or the 40% solution, times 15 liters. Here I chose to use substitution as a method of solving the system of linear equation. So the equation on the left, I solve for x. X is equal to 15 liters minus y. Substituting that in, we get 20 times 15 liters minus y, that quantity, plus 80y is equal to 600 liters. 300 liters minus 20y plus 80y is equal to 600 liters. When we subtract 20y and the 80 plus the 80y, we get 60y is equal to 300 liters. Y is then 5 liters. To find x, I go back to the left and substitute in. X is equal to 15 liters minus 5 liters, so x would be 10 liters. Now we make our conclusion. The chemist will need 10 liters of the 20% solution and 5 liters of the 80% solution. The next area is concentration problems. To talk about concentration problems in science, we need to look at a few terms. Molarity is an expression of the moles of a solute per liter of solution. Solute is a substance dissolved in another substance. In chemistry, a mole is the standard measure of amount. So M for mole is equal to moles of solute divided by liters of solution. To prepare solution concentration, we use the molarity of the first solution times the volume of the first solution is equal to the molarity of the second solution times the volume of the second solution. We'll begin by looking at a problem that asks for the mass of NaCl, which is sodium chloride. It's required to prepare a 1 mole sodium chloride solution. We find the molar mass. We know that sodium, we have 1 atom of sodium times, from the periodic table, it has a molar mass of 23. That equals 23. The chloride, again 1 atom, times, from the periodic table, 35.5. That's equal to 35.5, and we're going to add those together to get our molar mass. That's 58.5. Another problem. Calculate the molarity of a solution prepared by dissolving 4.09 grams of sodium iodide in enough water to prepare 312 milliliters of solution. We set up the table the same as the first one, finding our molar mass for both the sodium and the iodide in the periodic table. So we have 23 and 127 to add. That's 150 grams per mole. Now we're going to find the moles of the sodium iodine. So moles is equal to moles of solute divided by liters of solution. So we just substitute in what we have, the 4.09 grams divided by 150 grams that we got from the molar mass. That comes out to be 0.0273. Now we want 312 milliliters. We have to convert that to liters. It's 0.312. Now, putting that into our formula, we have 0.0273 times 1, which is the volume of our first solution, is equal to M sub 2, or the molarity of our second solution, times its volume, 0.312 liters. Divide, and we find out that the molarity in the second solution has to be 0.0875. Here's another problem. A 20-gram sample of hydrofluoric acid is dissolved in enough water to give 200 milliliters of solution. Find the concentration of the solution. We go through the table again, finding our molar mass, and it comes up to be 20. So then we're going to divide, taking the 20 grams of hydrofluoric acid and divide it by the 20 of our molar mass. That comes up to be 1 mole of hydrofluoric acid. Then we do what we did before. We're going to change the 200 milliliters to 0.2 liters. Putting that in our formula, we find that the molarity of the second solution is 5. Today we talked about mixture and concentration problems, understanding them, setting up equations to solve both of them, how to use different mathematical techniques to solve the equation, and to make conclusions about the solutions for the problems.